So let's try to understand refraction a little better. Why do we have this bending of light as it goes across an interface between two media, as it goes from one medium into another? Okay, so here's a picture which kind of explains it, I think, reasonably well. So what are we looking at in this picture? Okay, so we have to think of light going beyond just the simple ray model where, if you have a ray of light going in this direction, all that's saying is we have an electromagnetic wave which is propagating in this direction with a speed v1 in this direction. Okay, so the way you can picture the wave is with a collection of parallel lines. And what these parallel lines represent are points on the crest of a wave. Okay, so here's one wave front, and these lines that make up these points that make up this line represent the entire crest of the wave. In the space in between the lines, we have the trough of the wave. Here's another crest. Here's another crest. If you want an analogy, imagine you're at the beach and you're watching water waves go by, and if the water waves have crests that are parallel to each other when you're above looking down on them, well, these lines just represent the crests, the high points of the waves, and the space in between represents the low points. Okay, so these lines of points, these lines which represent the crests, they're perpendicular to the direction of the propagation of the wave. So all of these wave crests and troughs are moving in this direction until they strike the interface between the two media, and then something else happens. Okay, what happens? Well, okay, let's define a few quantities first. So for medium 1, v1 will be the speed with which the wave is propagating. Theta 1 will be the angle of incidence, the angle between the direction the wave is moving and the imaginary line that we call the normal, where the normal is normal or perpendicular to the actual interface. So there's theta 1. And the distance between these lines, well, we've said that these are crests of the wave. Okay, so the distance between these crests must be the wavelength, lambda 1. Okay? So the wave goes from this medium, crosses this interface, and then it continues along. Okay, let's not make any assumption about whether the angle, theta 2, which I guess we can call the angle of refraction, or we did call it that, I think, on the previous slide. Make no assumption about what its relationship is with respect to theta 1. You might guess that, well, I think it's probably equal, kind of like was the case for reflection. But don't make any assumptions. Just say, okay, it's some angle. We're going to figure out what that angle is. What we do know is that when the wave enters in the new medium, the wavelength is going to change. So we're looking at an illustration here where we go from medium 1 with a lower index of refraction. The wave travels faster, to medium 2 with a higher index of refraction, where the wave travels slower. How do we know it's traveling slower? Because, at least in this picture, in this illustration, the wavelength, the distance between the lines which represent the crests of the wavelength is smaller. Lambda 2 is smaller than lambda 1. Okay? We could have considered a case where lambda 2 was greater than lambda 1, but this is the case we're going to consider for now. Okay. So let's see what happens. Well, let's blow up this figure a little bit, okay? Because I want to refer to some triangles here. So again, this pink line is the line that the wave is traveling in medium 1, and this pink line is perpendicular to the lines representing the crests of the wave, okay? And it's the direction the wave is traveling in medium 2. Okay, and we know that, let's see, we've argued that these propagation directions are perpendicular to the lines representing the crests. okay, both for medium 2 and for medium 1. And if you think about it, that means we can construct a couple right angle triangles. Here's a right angle triangle in medium 1. And this side of the right angle, you'll notice, is the wavelength lambda 1. And here is the angle theta 1, which is the same as this theta 1. Okay, you might need to review your high school geometry, and you can use that to argue that if this is theta 1, then this angle in this triangle must also be theta 1. Okay? Likewise, you can argue that if we have another right angle triangle here, this side is the wavelength lambda 2, and if this angle is theta 2 here, then you can argue using geometry that this angle on this second right angle triangle must also be theta 2. Okay? So we have a couple right angle triangles. This side is lambda 1, this angle is theta 1. In the other one, we have this right angle triangle. This side is lambda 2, this angle is theta 2. But what you'll notice is these two triangles share the same hypotenuse. Okay? And we can use that fact. Whatever this distance is from this point to this point, it's the length of the hypotenuse for both of these right angle triangles. Okay? So that's what I say over here. The hypotenuse of both triangles is the same. And in each case, it's going to be lambda divided by the sine of, well, either theta 1 or theta 2. I'll just generically call either angle theta. Why is that the case? Well, okay, we may have to blow this up again. Okay, so if you consider this right angle triangle, we have this side, which is lambda 1, divided by the hypotenuse. Well, that will be equal to the sine of this angle, theta 1, because this side is opposite to this angle in the triangle. Okay, so the wavelength is equal to the hypotenuse. The ratio of lambda to the hypotenuse is sine of theta 1. That means the hypotenuse, if you think about it, write it down, you can write it as the wavelength divided by sine of the angle of the triangle. Okay, so whether we're talking about triangle for medium 1 or medium 2, it's the same thing. So lambda 1 over sine theta 1 is the hypotenuse. Lambda 2 over sine theta 2, it's the same hypotenuse because it's the same line here. And let's see, what do we know about lambda? Well, we argued before it was c divided by n times f. So let's replace wavelength, lambda 1 and lambda 2, with this expression. Now I'm going to have to put an index, a label on the index of refraction. Okay, a subscript on the number n, the index of refraction, because we have wavelength in medium 1. Okay, well, that wavelength means we are referring to the index of refraction in medium 1. Don't need to do that for f, because remember, the frequency of the wave does not change. That's the one thing that stays constant as you go from one medium to another. Okay, do the same on the other side of the equation. So we need an n2. We don't need a index, or we don't need a subscript on the f. So we have, after the substitution, for each of the two wavelengths, we have this expression. You'll notice that c and f cancel out either side. And if you simplify this equation, then take the reciprocal of each side, we come to the important equation, and this is what we wanted to derive. This equation is called Snell's law. So if you've taken high school physics, you've probably seen this before. If you haven't, well, here it is. And what it's telling you is a relationship between the angle of incidence and the angle of refraction in terms of these properties of the two media, the indices of refraction, N1 and N2. Okay? And you'll notice here, if you think about the consequence of this equation, you can show that it implies that if N2 is greater than N1, if the index of refraction for medium 2 is greater than that for medium 1, then theta 2 will be less than theta 1. Okay? So you can test that out. You can try a few different values of N1 and N2, and then see what that implies about theta 1 and theta 2. This is what you're going to find. So as you go from a lower index of refraction medium to one with a higher index of refraction, the light will tend to bend towards the normal. The normal, remember, is this line which is perpendicular to the surface, the interface between the two media. Okay, so this is Snell's law. So let's use Snell's law to solve a problem. Okay, so we have a problem here. Here's the relevant picture. Your keys have been dropped into a lake at night, flashlight held directly over the dock edge. So there it is. Dock edge and 0.5 meters above the water. Illuminates the keys when it is aimed at 40 degrees to the vertical. What is the horizontal distance, x, of the keys from the deck? So here are the keys here. And what other information are we given? We're given this, the depth is 1.6 meters. The flashlight is 0.5 meters above the surface of the water. And let's see, what else do we know? We know that, so what we are asked to find is the distance that the keys are away from the deck. So that means if we go directly below the edge of the deck here and we measure outwards along the x-axis to the keys, that is the quantity x that we're looking for. Okay? And we know that the ray of light coming from the flashlight, when it is at this angle of incidence of 40 degrees, and note that that's the angle between the light and the normal, not between the light and the surface of the water, but the light and the normal, okay, that's 40 degrees. So obviously what's going to happen as the light goes into the water has a higher index of refraction, so the light will tend to bend towards the normal, okay? And we could say that, and it bends towards normal, and eventually it settles on the keys down here. So what we're going to do is to use Snell's law to determine this distance x1 and this distance x2, okay? So you see how they're defined here. So the x1 is a horizontal distance from the flashlight to the point where the light hits the water. And x2 is a horizontal distance from that point. Okay, so drop down to the bottom of the water, the horizontal distance from that point to where the keys are. We're going to find x1 and x2 separately, and then we add them together, we'll get x. That's what we're looking for. Okay? So what's the starting point? The starting point, of course, is Snell's law. Here we have it. So medium 1 is air. So we have index of refraction for air multiplied by sine theta 1. Sine theta 1 is this angle here. We know that theta 1 is 40 degrees. Is equal to the index of refraction for water multiplied by sine of theta 2. We don't know what theta 2 is. Okay, we're going to have to find out what theta 2 is. So how do we find it? Well, we have everything in this equation except for theta 2. We have the two n's, the indices of refraction. We know what theta 1 is. So we can solve for theta 2. And I'm just going to leave it as the sine of theta 2. So the sine of theta 2 is, we'll divide each side of the equation, let's see, by index of refraction for water. And when we do that, we get sine theta 2 is the ratio n air to n over n water multiplied by sine of theta 1.